Uh-huh. Yeah, thank you very much. That was the crucial observation for today. Mm, okay, so last time we studied proper morphisms. And before we had affine morphisms, and finite morphisms. And in general, it is um, a rather deep idea of Grothendieck, who developed the modern language of algebraic geometry, that it is worth to study morphisms, at least not less than the varieties themselves. So, well, there is a category of algebraic varieties, and certainly there are objects in this category, the algebraic varieties themselves, and also the morphisms between them. And the philosophical idea is that the morphisms are not less, but maybe even more important than the objects. And then somehow we know how to view the objects, that is algebraic varieties, locally. They're glued locally from affine algebraic varieties, and these are just spectra of algebras. And now the morphisms also can be studied locally. In fact, if you remember the definition of affine morphisms, they were defined locally. Yeah, and the point is that in order to describe morphisms, say affine or projective, like pi from x to y, locally over y, we will need sheaves of OY module, or maybe OY algebras. Okay, so far we only encountered one sheaf, just OY itself. But from now on, we will need to use many more sheaves, and they will be all sheaves of OY modules. Okay, and in fact, not arbitrary OY modules, but some specific called coherent or quasi-coherent OY modules. So this is what we will actually study, but maybe let's begin with some other the simplest example of sheaf, which is not OY module and it's not coherent or quasi-coherent, namely the constant sheaf. So you take some set, say S, then have a topological space X, And then you take a constant sheaf S underlined. So I have to say what are the sections, right? And then maybe somebody knows what are the sections. For example, Sergey, do you know or can you guess what are the sections
Ну, постоянно абелева группа какая-нибудь.
Well, yeah, it's not necessarily an abelian group. It's just a set. Later on, we'll use sheaves with coefficients in abelian groups, right? But so far, we don't need any anything like this. Just a set. But also, you are welcome to imagine that the set is an abelian group. But if I understood you correctly, you just say that the set of sections of this constant sheaf over an open set U is just S itself.
Михаил Владленович, а ведь
Yes.
постоянный предпучок, он же не всегда пучок, он будет пучком только тогда, когда у нас всем открытые подмножества пересекаются.
Oh, right, absolutely, absolutely.
Поэтому нужно локальные константы брать. Да.
Absolutely, yes. So this is the wrong answer. So why is it wrong? Since it violates the gluing axiom of sheaves. Well, let me just formulate the correct answer. So this is, so to say, locally constant functions from U to S, or in other words, this is S to the power the connected components of U. Okay, so this is the correct answer. But what we have actually constructed in this naive, stupid way was just a pre-sheaf. Okay.
А что там за индекс у π?
Pi naught, it is the the set of connected components.
Спасибо.
So this suggestion is also sensible, and it is only a pre-sheaf. So in general, a pre-sheaf is well, in some scientific language, it's a contravariant functor from the category of open subsets of X with morphisms just open inclusions. So the contravariant function from this category just to the category of set, or abelian groups, or whatever you prefer. Okay, so this is a pre-sheaf, and just in normal language, it says that pre-sheaf say P. It is the following data. Any open subset goes to some set of sections P of U, called section of P over U. And if we have a smaller open subset, V inside U, then we are equipped with the restriction morphism from U to V, so from P of U to P of V. And certainly they compose transitively.
Извините, а может быть более естественно писать U вверху, а V внизу? Ограничение.
Okay, let's. Oops, sorry. Yeah, it may be so. Just like this. Yeah. Okay. Maybe, but I'm not sure I will keep this tradition. Okay. So the definition of pre-sheaf is certainly simpler, but somehow the experience shows that they're less useful. So sheaves are some particular kind of pre-sheaves, and this particular kind is most useful. Okay, so in fact, historically,
Можно вопрос?
Yes.
Мы, когда говорим, что у нас есть P2, мы вообще требуем какую-то структуру на P2 пока? Или вообще никакой не требуем?
No, nothing, just sets. But you can also consider pre-sheaves of abelian groups or pre-sheaves of vector space or whatever.
Хорошо.
Or modules or something. So historically, the first sheaf was the constant one. And then the locally constant ones, and they were introduced by Jean Leray in about 44, something like this. And once again, we will study something rather different. Our sheaves will be not constant, not locally constant, but rather coherent and quasi-coherent. So they appeared only, well, maybe let me say that coherent sheaves appeared in 10 years. So they were due to Jean Pierre Serre, around 1955. And we will study those. Okay, but about Jean Leray, it's a funny story. Maybe you heard it, but just in case, let me say a few words. But he was already a very famous French mathematician, but certainly it was the World War II, so he had to fight as a French officer, and then he immediately was interned as a prisoner of war, and he spent the whole Second World War in some German detention center as a prisoner of war. But the conditions there were rather nice, so he was able to do mathematics. So his main topic was some differential equations like hydrodynamics, but he was afraid that if he continues doing hydrodynamics, it could be used by Germans in order to improve their military equipment, say submarines or whatever. So he was very cautious not to do anything that could be potentially useful for military applications. And he decided to do some topology instead that would have no applications whatsoever. And doing topology, he came across this notion of sheaves, but then later on, it turned out that this notion perhaps had most of applications. Among the discoveries made in 20th century, perhaps sheaves was one with the most applications, quite paradoxically. But still, as far as I know, they don't have any applications in military science. So in a sense, Leray was right. Okay. Okay, so now let's go back to sheaves and pre-sheaves. Some of the idea is that pre-sheaves are, well, they don't have these extra conditions of gluing, so they are more manageable. And we will introduce certain operations, how to construct new sheaves and morphisms of sheaves, like pullback or push forward that you could encounter in your home assignment. And the point is that when you define those operations, you first define them on some naive level, and what you get are usually not sheaves, but just pre-sheaves. But then you somehow improve your pre-sheaves, and you produce actual sheaves from these pre-sheaves, and this is what you really want. Okay, so this is the general strategy. Well, again, in the scientific language, we have the category of sheaves and category of pre-sheaves, and well, maybe I have to say that morphisms of sheaves or pre-sheaves well, they're just morphisms in the most naive sense. So if you have like P1 and P2, then this means that for any open set U, you want a morphism of sections from P1 to P2 of U, commuting with restrictions. Okay, so here the definition is the same for sheaves or pre-sheaves. You don't use this gluing property in any way. So we have an evident embedding.
Можно спросить?
Yes.
Что такое естественный морфизм?
Natural morphism. It depends on the context. And so in which phrase have you encountered natural morphism?
Ну, например, вот в домашней работе было упражнение, что прямой обратный образ пучка есть, естественно, отображение в этот же пучок.
Yes. Well, on the one hand, it should be a morphism of functors. So there is the identity functor and the composition of pullback and push forward, and it must be a morphism between functors. So it must be, well, must commute with other morphisms. But on the other hand, for example, you could produce the zero morphism, yeah, from one sheaves to the other, and this would be a wrong solution of the home assignment problem. So there is no mathematical rigorous definition of natural morphism. It should satisfy all the possible compatibilities, but it's not enough. It's not quite a rigorous mathematical.
Can we think about natural as about nice defined? So it can.
Yeah, I like this much more. Yeah. That's a very good definition. Yeah.
Спасибо.
Welcome. So we have a sort of forgetful functor. F from sheaves on X to pre-sheaf on X. Yeah, I mean, sheaves are pre-sheaves with certain gluing conditions, and we just ignore these gluing conditions. So certainly each sheaf is a pre-sheaf, and this is just it. Okay, and the point is that this functor F admits a left adjoint. Sorry, the left adjoint. Say S from pre-sheaves to sheaves on X. So what does that mean to have a left adjoint? It means that given a pre-sheaf, say P, and a sheaf F. So F is because Jean Leray was a French mathematician, and in French, sheaves are called faisceaux. And by the way, this is the same root as in fascist. So given a pre-sheaf and the sheaf, the morphisms from this sheafification, left adjoint functor of P into F are the same, and these homes are taken in the category of sheaves, are the same as homes from P to this sheaf F that is with its sheaf structure forgotten. The home is taken in the category of pre-sheaves.
Excuse me, but is home of two sheaves same as home of two of them as pre-sheaves?
Yes, absolutely. Yes.
So we don't really care about category.
Yes, we don't. One category is just a full subcategory of the other one. Okay, so this S is called sheafification. And there's one instant when the Russian language is better than English. I think in Russian it's called пучкование, somewhat simpler than sheafification. And there is some explicit construction.
Обычно говорят пучковизация. Это не
But
сильно
then
проще.
it loses any advantage over English. Пучковизация is not better than sheafification.
Можно
Okay.
еще раз, откуда у нас тут S появилось?
So I am going to say how S is defined. Yeah, but then it isn't somehow in your work with sheaves, you will actually never really use this particular construction. You will only use this property that it's left adjoint to just forgetting sheaf structure. Okay. So the construction.
Почему он существует? Или мы сейчас будем строить его?
Yes.
То есть мы сейчас хотим его построить.
Yes. So first of all, you will need a few important notions. So first is the notion of stock. P sub x at a point x in our topological space. So this is the direct limit over all open neighborhoods of x, but shrinking, becoming smaller and smaller, P of U, local sections. Okay. So, in other words, yes.
Верно, что вот этот прямой предел — это то же, что копредел для некоторой чум-диаграммы.
Right. It is nowadays called colimit. So any section, say sigma, in P of U, in case U contains X, defines an element in this stock. Okay.
Как мы определили этот предел?
Well, let me not answer this question. You may look it up in Kempf. The definition of colimit or direct limit or whatever you should look up, say in Kempf or in Wikipedia or
in Kempf was nice definition of stalk without any categorical things, that it's just equivalence classes of sections.
Absolutely, yeah, that's the definition of colimit, right? Okay, so let's consider an example. When our pre-sheaf is actually a sheaf, and it's the structure sheaf of an affine algebraic variety. Okay, so we have a point x. X corresponds to the corresponding maximal ideal. Okay, and then we see, since a basis of topology of our X is formed by the opens D sub F. The opens containing X they correspond to the functions f such that f of x is not 0. So in other words, f does not lie in the maximal ideal corresponding to this point. Okay, and from this you deduce that the stock of our structure sheaf at point x is the localization of A at this maximal ideal. So it is denoted AX, and it is actually A with all S in capital S inverted. And here capital S is some multiplicative system, namely the complement to the maximal ideal. So you invert all the functions that are not vanishing at the point x. In other words, that are not in the maximal ideal. Okay, they certainly form a multiplicative system. I mean, that's closed under multiplication. And then you invert all of them. So you almost take the field of fractions of A. Yeah, you invert most of functions in A. You only do not allow to invert the functions which vanish at X. But anything else you do invert. Okay, so this is an example of stock. And you see the stock is big, and you should not confuse it with fibers. Okay, so we didn't speak about fibers yet. We will next time and from next time on. But the fiber of OX at the point X is just complex numbers. Okay, so it's very small. And the map to fiber is just the value of your function at X. Okay, but the stock is very big. Yeah, you have this stock AX, and it contains A, but then A maps onto this fiber. Well, I don't have a notation for the stock, but it's the fiber. Okay, so anyway, that's the notion of the stock. But maybe one other example.
Извините,
Yes.
а вот действительно ли вот этот слой это есть копредел, когда согласовать с тем определением, которое было?
Stock certainly is a colimit, yes.
Ну вот почему вот эта локализация это действительно некоторый копредел?
Well, I will answer almost no questions today, because if I try to go into all the detail about sheaves, it will take us all the rest of the class till New Year, and I don't want to do this, so I will only mention everything very shortly, and I will not answer such questions. So for the constant sheaf.
Можно вопрос? Почему вы написали, что там C, у нас разве теперь поле двойной комплексный числа?
Yes, sorry, it's my usual mistake. Yeah, sorry. Just the base field K. So thank you.
Почему слой будет K?
Well, we didn't formally introduce fibers yet. When we introduce them in a couple of times, then you will see that it's absolutely clear. For the constant sheaf as underlined, the stock.
Разве в этом случае это не очевидно? Это же просто фактор алгебры по максимальному идеалу.
Yes, certainly it's absolutely evident. If you know in advance, then everything I said today is absolutely evident. Yeah, I apologize for this. So the stock of this sheaf at the point X is just S itself. Okay, so for locally constant sheaves, the stocks are rather small. They do not grow bigger. By the way, one other remark about these stocks is that they are not finally generated anymore. You see, somehow we managed for 2 months to live in the realm of finally generated algebras. Yeah, but then taking stocks now takes us out of this safe realm, unfortunately. Maybe let me also say this. AX is not finitely generated. So, for example, you cannot take its spectrum in the sense we discussed before. Yeah, because whatever we discussed only made sense for finally generated algebras. Fine. So this was some discussion of stocks. Okay. Now the next notion. Let me see. What was it? It was number 1. You see the stocks. And now let's go to number 2, maybe. The sheaf of discontinuous sections. This is something very stupid. It's sort of sheaf of
Можно
functions.
вопрос?
Yes.
Вот там мы писали, что константный пучок, мы же вроде как-то поняли, что это предпучок, нет?
No, but I tried to deceive you, giving a wrong and naive definition, but then everybody knew the correct definition, and they corrected me, right? And as underlined means the sheaf, the constant sheaf, not a pre-sheaf. So the sheaf of discontinuous sections is a sort of sheaf of functions, but the only minor issue is that these functions do not have standard values. I mean, when we studied our algebraic varieties, we only talked about functions with values in our base field K. And now the functions take different values at different points. I mean, at each point, they take values in the corresponding stock. Okay? So, say, maybe let's call it D P of U is the set of functions. And there's no notion of continuity or algebraicity or whatever, just any functions, absolutely arbitrary, any functions. So a point X goes to some f of X in the stock Px. Okay. But once again, the stocks at different points are different. There's no way to compare them. So the values of functions at different points lie in different sets. But still, they are functions, and for this reason, this is a sheaf, just for trivial reasons. dp is a sheaf for free. And certainly there is a natural morphism. From P to dp, right? Just when any section goes to its value at any point, right? So sigma goes to the collection sigma x x mu.
Excuse me, and P
Yes.
is an arbitrary pre-sheaf
P
that
is
was
arbitrary
before. Yeah?
pre-sheaf, yes. P is an arbitrary pre-sheaf. Okay, and then finally, the desired construction is that the sheafification of P is the smallest subsheaf in dp, containing the image of P. Okay, but so in, so to say, in plain English, what was it? F lies in SP of U if U is the union of some smaller, that's UI, and F restricted to UI, and we had this notation, but I forgot what was the sub, what was upper index, lower, and upper. I forgot. Say from U to UI of F. Comes.
По идее, наоборот.
Okay, I am ready to admit it. So comes from an actual section sigma in this pre-sheaf, maybe sigma I. Okay, so now you, so in plain English, you just enforce this gluing condition. Okay, so I just said nothing else. Yeah, I just said that you allow your sections to be glued from smaller open subsets, and that's it. Okay.
Не совсем понял, а почему вот аксиома склейки будет выполняться, что если у нас есть какие-то сечения, S-итые, S-житые, согласованные на пересечениях, почему найдется такое S глобальное, которое будет...
All such questions are readdressed to Kemp. Just read his book. Or in fact, there are many nice expositions. Say Hartshorn book. Maybe it's formidable as a whole, but this particular chapter or section about sheaves is very nice. So I strongly recommend to look into Hartshorn if you are not satisfied with Kemp for some reason. Also say Griffiths Harris and many other places have nice expositions of sheaves.
Сейчас, можно вопрос?
Yes.
А вот ДП, он является пучком? Ну, сам?
Oh yes, certainly. Just for trivial reasons. Yeah, because it's just functions. Any functions form sheaf. Just for trivial reasons. If you think about it, it's absolutely evident.
Okay.
You can glue functions. Yeah, just so any pre-sheaf of functions is a sheaf. It's for free. Okay. So far so good. Now let's talk about sheaves of abelian groups. And the main point is that they form an abelian category. Sorry. So we have to define whatever injections, surjections, or epimorphisms, monomorphisms, and kernels and co-kernels and images. So here, monomorphism or embedding or injection are just embeddings of sections on any open. So you say that a morphism from one sheaf F1 to F2 is an embedding if and only if F1 of U to F2 of U is an embedding for every U. Okay, so that's easy. But for surjections or epimorphisms, it's not as easy. So maybe more generally, let me say when say what is a morphism. So if you have a morphism from F1 to F2, maybe let's call it phi. Then you can take a naive image. So you may say that naive image of phi values at any U is just the image of phi from F1 of U to F2 of U. But then this thing will be only a pre-sheaf. In general. Okay, and the actual image of phi is the sheafification of this naive guy. And again, this is the smallest subsheaf of F2 containing this naive image. Okay, and now we have we have I think we have defined this abelian category structure. Yeah, so maybe let me also say about cokernels. But I essentially just repeat what I said. So we have the same map from F1 to F2. And I have a naive quotient, so naive cokernel of phi. The sections at U are the quotient F2 of U modulo phi of F1 of U. Okay, again, this is a pre-sheaf. And its sheafification is the actual co-kernel of phi. Okay. So then there is a very useful fact that a short exact sequence can be detected at the level of stocks. So the morphisms between three sheaves form a short exact sequence. This means that say D1, D2. So D1 is an embedding, and D2 is a surjection, and the image of D1 equals the kernel of D2. Hopefully, you heard this many times already. So this is so if and only if for any point the induced sequence of stocks is also exact.
Скажите, а почему после пучковизации у нас в большинстве случаев не будет оставаться что-то нетривиальное? Ну, и мы предпучок пучковизуем. Почему в большинстве случаев что-то останется после пучковизации нетривиальное?
But you see, somehow sheafification only makes your thing bigger.
Like we add all gluings. We can.
Yeah, because we add all gluings. Yeah.
Спасибо.
There's no danger of obtaining zero. Okay, so maybe let's consider an example. This is holomorphic diagram complex on the punctured line. So you have the sheaf of functions, but these functions are analytic. So I mean locally analytic, locally holomorphic. Okay, and you have just the Durham differential that goes to one forms, and they are also analytic. In fact, maybe in December we'll have some algebraic notion of differential forms, but so far probably we don't have anything else. So I claim that at the level of sheaves, this is surjection, and there is some kernel, and this kernel only consists of constant functions. And since we're speaking of holomorphic, then certainly the base field is complex numbers. So now I am legally allowed to write C instead of K. Okay. And well, this is just embedding of constant function, or maybe locally constant functions, if you wish. Okay. So this is an exact sequence of sheaves, and here you have a global section.
Excuse me. So naive image of C will be constant function, but real image with sheafification will be locally constant. Yeah.
No, I mean, if you have a connected open subset, yeah, the sections of the constant sheaf are just constants. Yeah, but if you have in analytic topology, you might have an open subset with a few connected components. Yeah, for example, like strictly right hyperplane or strictly left half plane, right? You just remove the imaginary axis. And then on this open subset, you can have locally constant functions. Let's say the function which is equal to 0 on the right half plane and to 1 on the left half plane. Okay, that's perfectly legitimate. And among the global sections of one forms on the punctured line, there is the best loved form like this, dz over z. Okay, and that's a global section, but certainly it's not in the image of D. Okay, so this is not df for any f that is a global section so in other words, it's a holomorphic function.
Поле у нас комплексное.
Oh yes, on the punctured complex line or plane. Okay, you all know this, but so once again, being surjective at the level of all stocks, or being surjective in the sense of sheaves, does not mean being surjective on all the sections. Okay, it's only true locally. So locally it is surjective. I mean, there is a cover. That this punctured line is some union of open subsets, and on each open subset there is a function function fi such that the differential of fi is exactly this dz over z, but on ui, but not globally, only locally. Yeah, and in fact, I hope everybody knows what this cover must be. So what is the condition on this cover in order to guarantee the existence of those primitives FIs? Say, Vanya Ukrainцев, can you tell me how to guarantee this existence? What do you have to demand of those UIs? Vanya? Or maybe Wei Chen, can you tell me what do you have to demand of UIs? Or Vanya, yeah, tell me. I don't hear you so far.
Сейчас слышно?
Yes.
Хорошо.
So what is the answer?
Ну, такие уиты, которые как-то...
Yes?
Сейчас.
Односвязанные.
Right, absolutely, yes. Those UIs must be simply connected.
Почему?
All the questions to Kempf or to Griffiths-Harris or to Sergei Lvovsky, maybe. Okay. Now,
Да, вот это мы сейчас показывали, что у нас нету сюръекции глобальной, но...
This was sort of counter-example. So I defined some fancy notion of surjection of sheaves, but this is not naive. It does not mean that on any open set, the sections surject. Yeah, they only surject locally. And if you go to the very end of localization, you just check it on the stocks, and it works on the level of stocks. Okay, but it does not work on the level of global sections, only on the level of local sections. Okay, so the notion of injective maps of sheaves is naive. It works just on any open set. but the notion of surjection of sheaves is not as naive. It does not work on any open set, only on small enough. Okay. Now, what else? So there are some sheaves that are good for naive people. So they're called flabby sheaves.
And what's Russian word for this, by the way?
Russian translation of flabby, yeah?
Yeah.
That's the question. It's valley. Valley. Okay. So by the way, if you open this book of Hartshorn in Russian translation, there you will see valley пучки and many other things. So the definition is that there is all the restriction maps are surjective. From U to V, from F of U to F of V is surjective. For any V inside V. Okay. In fact, it is equivalent to demanding that the restriction from global sections to anything else is surjective. Okay, just because of the transitivity condition on restrictions. Okay, and then for these guys, the surjectivity is true in naive sense. In the most naive sense. Namely, maybe let me provide as a fact that if F1 is flabby, and we have an exact sequence from F1 to F2 to F3 to 0, then this sequence on all the open sets is again exact. For any U. Okay. And
Обратное справедливо?
maybe, pardon me?
Обратное верно?
But I don't quite understand what could be a converse statement, but maybe let me formulate.
Если есть нижняя последовательность, то есть верхняя точность, верхняя последовательность.
Yeah, that's for sure, but somehow that's well, yes, it's true. So another fact is that if in this sequence so again we have this short exact sequence F1, F2, F3, 0, and F1 and F2 are flabby. Then F3 is also flabby. Okay, so this is a nice exercise. Well, but it's done in as far as I remember, in camp, but you may do it yourself. It's a nice exercise. Okay, so now we have 15 minutes left, so let's move to quasi-coherent sheaves. On algebraic varieties. And in fact, this will be our topic for the rest of the year and for the rest of our lives, whatever. We'll continue to study those quasi-coherent sheaves. We start with
F1 и F2.
And what are your doubts? What would you?
F1 и F3. Нет?
Oh no.
Ладно, видимо.
I think that is correct as stated. Okay, so we start with the only sheaf we have so far, OX, and now we can. So now we'll consider the sheaves of OX modules. So the sheaves F such that for any open U, the space of sections F of U is equipped with the action of the space of sections of the structure sheaf. Okay, in a compatible way. Okay, so when I say in short just OX module, I mean that we are considering a sheaf of OX modules in this sense. Okay, but our shortcut will be just OX modules. Fine. Now, for example, the sheaf OX itself certainly is an OX module, and it's a free OX module of rank 1. Okay, but we can also consider, say, OX to the direct sum n. It's a free OX module of rank n. Okay, now we can also consider locally free OX modules. So these are sheaves such that there exists a covering. And the restriction of F to UI is a free UI module.
Сейчас мы считаем X это кольцованное пространство или уже даже
Oh
алгебраическое?
yes, the algebraic variety, just whatever you like. Yeah, an algebraic variety. Okay, so an example that we discussed in the end of the last time. There was a line bundle, one-dimensional vector bundle, or in other words, line bundle. That's tautological. O of -1 on Pn. Yeah, so over any point the fiber of this. Maybe let's denote it V. So the fiber at any point is the corresponding line.
А так, наверное, можно перепутать слой и росток, если так писать.
Yeah, you
Мы
are right.
обозначали росток через x. Значит, p минус первое от x. Это будет слой.
Let me just write here the fiber and let it be this way, because there is no standard. There is no other standard notation different from this. And unfortunately, there is some confusion in notation. So the fiber is the line in the ambient vector space corresponding to x. Okay, and then our sheaf, say M, is the sheaf of local sections of this line bundle V. Okay.
Слой будет только одна линия или будет все линии, проходящие через точку?
The points in projective space are just line. Yeah, but by definition.
Да.
Okay, so given a point in projective space, I consider this corresponding line. Okay, that corresponds to this point. Just this one line.
So answer is that line has 0 to not only x.
Oh yeah, yes. This is just a linear line. Yeah, not a fine, but linear line passing through 0. Yeah. Okay. So this line bundle is locally trivial. Yeah, if you remove a hyperplane from Pn, then on the remaining open set, V restricted to Pn without Pn minus 1 is isomorphic to this base times just A1. You can find such a trivialization, and hence all the sections will be just functions. You see, the sections of trivial A1 bundle are just functions, and in this sense, this sheaf of sections will be locally trivial of rank 1. Okay, but it's only locally trivial. Globally, it's not trivial at all, and say there are no global sections at all. Say the sections M of Pn itself are just 0. I mean, there is no way to coherently choose a vector in any line. Okay, so this was the notion of locally free sheaves. Okay, and now the central notion, a quasi-coherent sheaf. Again, M. Sorry. Of X modules. M is locally the co-kernel of a morphism of locally free sheaves. So in other words, again, there exists an open cover. And on this open cover, you can take some morphism phi sub I from O ui to some power, say I. And in fact, this power can be even infinite. Yeah, it's not necessarily finite. If it's finite, the sheaf will be called coherent. And these are just quasi-coherent. So they may have infinitely many generators and relations. This such that the restriction of our sheaf M to ui is the co-kernel of phi I. Okay. So in other words, it is given by generators say J many and relations say I many. Okay, so the quotient of this locally free OJ by the image. I'm sorry. But by the image of this locally free OI. Okay, and well, just one way to construct quasi-coherent sheaves. This is so-called localization. Namely, suppose we have the global sections O x of x, and this is A. So if x is affine, so if it's the spectrum of this A, then it'll be especially nice, and we will study this next time. In this case, the localization will be an equivalence of categories from A modules to quasi-coherent OX modules. In general, it's not so. Say X can be projective or proper variety, and then the global functions will be just constants, and you will not see much from this. But still, you do have some localization. And suppose M is an I module. And then you can consider its localization. It's a sheaf. Of OX modules. And namely, well, maybe let me call it M script. So M of U is the sections of the structure sheaf over U, tensored over global sections with M. Yeah. So you see that the global functions, they act on M by our assumption, but they also act on the local functions by restriction, right? So you can do this. And this will be a quasi-coherent sheaf. But now I see my time is over, so we'll discuss this from the very beginning next time. And I will prove this great theorem that localization is an equivalence of categories for affine algebraic varieties, an equivalence of categories from modules over the global sections to the quasi-coherent sheaves on the spectrum of this algebra. So that's it for today. Thank you. And next time we will be much slower than today, I promise. So I'm saving the notes. I'm stopping the recording. Yes. Yeah.